So after we do this really hard exercise trying to divide 64-bit numbers, let's have a little bit of fun. And so the next couple of exercises are actually how do we work with the internals of the Linux system? How do we actually manipulate Linux to do different things? And so far, the only things that we've really done is that we have been able to write to standard out and exit a program. But it'd be great to read from some places too, wouldn't it? To actually input data into our program other than just writing it in the source file. And so let's do that. The problem is, maybe, I guess, kind of a problem, is that when we get past things through the command line, when it's something that the user types, is that it's ASCII data. And so if we want to do anything numeric with that ASCII data, what we need to do is we actually need to write the opposite of our integer to ASCII. We actually need to do an ASCII to integer. But after that, it's all downhill. It's super easy, kind of. So let's actually start with that. Let's actually work with our ASCII to integer aspect first, and then work on this because it'll be a lot easier if we can just take this code and put it in a different file. And so let's create a to I.s. And I'm just going to put a simple header up here. We're going to say converts an ASCII value to integer. And the inputs that we're going to need are just the address of the string. So we'll put R0. And then we'll eventually output. Let's just output the integer value and we'll put it in R0 as well. We'll return it in the first spot. So I think this is the first time that we've actually written a module like this. And the first thing that we need to do is we need to tell the compiler that, or the linker, that we have this function in this file and that we're allowing you to use it. And we'll call this ATOI, A2I. And so we're going to put the global directive, but instead of using start, because this isn't going to be a main file, we're going to put A2I. And then, of course, we have to put the A2I label down here so it can find it. So the first thing that we need to do is we need to think about how do we actually accomplish this. And it's not as hard as you would think. If we read the numbers in order, all we have to do is take the number, figure out the integer value, and we can do the opposite of adding to the zero ASCII. We can subtract from the zero ASCII. And we add that to the total. And then all we have to do is multiply our total by 10 and add the next number. And then multiply by 10 and add the next number. Multiply by 10, add the next number. And so in a way, it's almost a little bit easier. And so what do we actually need? We need registers. We need something to hold the total. And we're going to put that in R4. The next thing that we need is, if you remember when we talked about the multiplication instructions, we can't use immediate values with that. We have to store numbers in registers. And so we'll use R5 to store 10. And that's the only thing R5 is going to do. And then we need to have a place for the address. We're going to copy the address out of R0 so that anything that we do doesn't directly affect it. And we also need a place to put the current ASCII value that we're reading. So we'll put, for R6, we'll do the current number that we're reading, and then R7 will be the address. We don't need to put the address in R7. It's more if we called another function within this function, if we kept it in R0, it could be wiped out by the other function. And so in this instance, it's not needed. However, it's kind of a good habit to get into is that if you're going to use something, move it to one of the later registers so that it's not in that R0 to R3 range. So the first thing that we're going to do is we're going to use our push, and we're going to push the registers we are using onto the stack to preserve them so that we don't overwrite something that the other program was using. And so we just do that with R4 to R7, just like that. And then what we need to do is, again, you don't need to technically, but, oh, actually, in this instance we do, because we don't have a guarantee that R4 is going to be empty. And so when you push something onto the stack, it doesn't clear the register. It just makes a copy of it onto the stack. And so in this instance, after all the times of me apologizing about how you don't actually have to do it, you do have to initialize this total to 0. I don't feel vindicated, but I feel like a little part of me makes sense now. The next thing that we do is load 10 into R5 for our multiplication. And then the other thing is just moving our address to R7. And we can use a move command because we're moving between two registers. And that's all the setup we need to do. We don't need to initialize R6 because we're going to be using R6 every single time. It doesn't do any kind of counter or anything like that. The total is going to be constant throughout every loop, so we need to initialize that. The address is going to be constant through every loop. Well, we're going to increment it, but it's constant, so we need to initialize that. The 10 constant, I guess we don't have to put it up here, but we waste an instruction if we put it in the loop. But the byte that we read is going to be a unique with every loop, so we don't need to initialize it up here. So let's write a loop. The benefit of putting code in a separate file is that labels only have to be unique within files. And so by creating a module like this that branches and links, we can use labels that may be used in the calling code without any conflict. So the first thing we need to do is load the first number. And we'll do that with a load byte. We're going to put it into R6, which is the current number, the address of R7, and we're going to increment the address after we read the byte. The next thing we're going to do is we're going to compare what we read to 0, and if it is 0, then we've got to the end of the string. We've hit a null character. And so we actually may want to put up here, first of all, it's an unsigned integer. But more importantly, instead of ASCII value, we should just actually explicitly say null terminated string. You want to give as much information to the person that may use this next as you can. And so if we're terminating this loop by the null character, we want to make sure that that's explicit in the header of this function. Yeah, so going back, we check if we have the null character. If we have the null character, we want to get out of here. We want to branch if equal and go exit. If we don't, what we want to do is we want to take our total and multiply by 10, so it moves everything over. And so we'll use the mul. We're going to store this in R4, which is our total, and we're going to multiply it by 10, so R5 and R4. And so this is kind of the same thing that we do when we left shift in binary, is that we're moving everything over one digit. But because it's base 10, then it's a multiply by 10. If you think about it in binary, when we shift over, we're actually multiplying by 2. We're multiplying by the base. And then we have this ASCII value in R6, but to get the integer value, we're going to subtract the ASCII value of 0. So this is the exact opposite that we did when we were trying to assign an ASCII value to an integer. We'll just put it right back in R6. And then all we have to do is add this to the total. And then we go back to loop. And I want to say that's probably a little less painless than than what we were doing before, going from integer to ASCII. So all we have to do is now write our exit. Because this is a routine that's going to be called, we don't have to write anything. We don't have to exit or anything like that. We just have to set up our output. And to do so, we're going to move into R0, the total, which is R4. And then we need to restore the registers that we pushed before, which is R4 to R7. Like that. And then branch and exchange with the link register. And so that should be everything that we do with that. Let's go back to our main file. Now that we've got the hard part out of the way, creating an ASCII to integer implementation, now we just need to figure out how we actually get the data from Linux and into our program from the arguments. If you look at the picture on the website, you can see that that little box is what the beginning of our stack looks like when our program starts. The stack, you can go read about the technical decisions of what a stack does and what it is, but very basically, a stack is where you want to put values that live longer than would be in a register, but shorter than you would have in memory. Therefore, pseudo-temporary values, I guess. You can see that when Linux gives us the arguments, the stack pointer is what points to the top of the stack. When we get these values from Linux, though, it's important to know that the stack doesn't have the actual values. And so if you look at the image, you see that the first value, it says it's 4. But the value that's actually on the stack is the address before the arrow that points to a memory address that has the value of 4. And so when we work with this, we have to know that everything that we're accessing is an address, which makes sense because in the next line down, when we have the executable path, it makes sense that that wouldn't be a single value and that'd be an address to the values so that we know where to start reading from. So let's actually start this. Again, we'll start with our global start and our start label. And so the first thing that we need to do is we need to actually get to our first address of information that we have, the first number that's inputted. And there's a couple of ways we can do this. One, we can pop 2 values off the stack, and then the next one that we pop off will be the address of our first number. The other thing that we can do is we can actually just add 8 to the stack pointer, and it'll just move that stack pointer down for us. And so we'll just do that. You can use the register number for the stack pointer, but you can also just refer to it as SP for stack pointer, the same way that we referred to the link register as LR. So I add 8. And then let's do our actual loop. You also notice that the arguments are a null-terminated set of data. So even though we have the number of arguments in the first parameter, or the first part of the stack, we can just loop through the arguments and get to the null part, and we'll be done. So the first thing we need to do is set up the ASCII to integer that we just wrote. And what we're going to do is we're just going to pop a value off the stack. And what that means is it's going to take what's off the top of the stack and put it wherever we want it. And so we're going to say pop, and we're going to put this into register 0, because for our ASCII integer, the only parameter that we need is the address of the ASCII representation of the number, and we'll just put it right into register 0. The next thing we need to do is actually figure out how we're going to get out of this loop. And as I said, it's a null terminated list, so we can just compare. If R0 is 0, then we can get out of it. And then branch if equal, and again, I'll use my exit label. And what happens is if we don't have a null value, then we'll just call our ASCII to integer. And that was the only thing that we need to provide to it, was the address. And then it'll return the actual integer value to us in register 0. So we need somewhere to create a total. Let's come up here with our registers. And again, I'm just going to initialize this. And we're just going to add the result from our ASCII to integer to the total. And then do an unconditional branch to the loop. So now we have a integer value in register 4. But if we want to display it, then we have to convert the integer back to ASCII. And so we'll use our integer to ASCII code. The two arguments are first the number that we want to convert, and then the address space for the output. So the number we want to convert, we'll put in R0, and that's the total in R4. And then we need to set up some space down here for the output. And then 11 characters, because the max for a 32-bit number is 10 digits plus the line ending. And then we'll load register here into R1. And then we will call our integer to ASCII. Like that. And now we have in our memory the ASCII representation of our number. And so all we have to do now is write it and exit the program. For our write, it's 4. First parameter is the file descriptor, which is 1 for standard out. The second parameter is the address we want to write from. And then the third parameter is the length, which is 11. SVC 0 to make the call, and then we just need to exit our program. One is exit. Only parameter is the error code, which is 0 for no error. And then SVC 0. And then that should be it. Let's try building this and running it. Oh, I know what I did. I put a colon here and there shouldn't be a colon. Try it again. Good. And if we run it, so let's try the numbers 3, 4, and 5. We get 12. Good. Let's try some other numbers. Let's try 12 and 45 and 56. No, because I can't do them in my head easily. 12, 45, and 45. 102. Good. So it looks like everything is working correctly. So that's how we read things from the command line as arguments. Let's try doing it from user input.